Actually, the presentations are all pretty short, so I think we'll actually end earlier than the
early time. Okay.
Maybe hit a happy hour before dinner. Yeah.
You know, if we must.
I'll let you know real quick what I did here. So we're just going to talk about that during the chair slides about those documents, and they're going to do a quick update on them. And this is all I put for what to do about them. We have this milestone for it.
Okay.
And we did a last call, and we issued it back in August, so it's been 2 months.
Yeah,
but that was just for the pharmaceutical testing. So are they done? I think everybody kind of agrees that we're pretty much done.
Yeah.
With the testing, I don't think it's probably.
There were some things that we're still working on in terms of, and I have to always like look it up or ask Thomas. There was one thing they weren't happy with, was like the temporal scaling or something like that.
I know they're changing the number of RD points, and they're also changing. There are open issues in the testing for sure, and there's the big elephant is when Netflix proposed this new metric, and we haven't really fully consumed it yet to see whether or not it's something that we should start adopting as our test criteria, the VMAF metric.
Oh, right.
So that's probably a big open issue too. We're going to try to close that before we finalize the document. Actually, it'd be good to see how the credits are faring on that metric. I've never seen a plot of the VMAF metric on any of the below or even AM values.
Well, that'd be where we ask Tim. What's the VMAF?
VMAF.
The VMAF. Is this something we could like produce graphs for? We could produce graphs for?
We could produce graphs.
Okay.
Is it in our compressed yet?
It is not currently in our compressed.
They released the source?
They released the source. I think the problem is
Video what?
Compute?
So when we wrote an actual fashion that we discovered every sub-metric that they feed into their neural network training has
So
that again when we get into your testing section.
yeah. All right, so we're a few minutes into the time slot. If I could ask someone near the back of the room to close the door, it's still a bit noisy out there. You're a NetVC looking around at the faces. I think you all intend to be here. This is the note well statement. Note it well. If you have any IPR and you're going to be discussing things at the microphone, make certain you understand what this means. If you do not understand it, consult your lawyer. We need a note taker and someone to sit in the jab room. As you'll see, we have 5 remote participants here. And mostly what we need for Jabber is if someone makes a comment, bring it to the microphone. Thank you very much, Jonathan. And we also need a note taker.
That's always the tough one.
Is what we need mostly captured are if there are decisions made, yes. Steve, can I lean on you? Thank you. Much appreciated. Steve Bosco has agreed to. Oh, well, we'll take Nathan's notes also. Thank you very much, Nathan.
And note takers, you can just put those directly in Etherpad if you want.
All right, so that's the administrative tasks. Actually, where are the blue sheets? Are they out already?
Yeah.
Okay, thank you. So the agenda today, we're going to talk a little bit about what we want to do with the requirements and testing documents, and then just a real quick overview of the changes in those 2 documents, probably 10 minutes or less each on those. We're going to get an update on Thor, a similar update on Dala, and then a discussion of using PVQ outside the dollar codec. Any comments on the agenda for today? All right, moving on then. I'll go ahead and let you take this, Mo.
Okay, so our first milestone back when we chartered was to perhaps publish an informational document on requirements and maybe another informational document on the testing and evaluation criteria. And we're kind of past that milestone by a little bit, so we should decide what we want to do about that. The first question really is whether or not we think there's value to publish these documents. They would only be informational, so whatever actual codec spec comes out of this effort would not have any normative dependencies on them, but there may be value in referring to these documents to avoid a bunch of descriptive text in the actual codec specs about what the motivations for some of the coding tools and choices are. So we'd like to hear about, first of all, is there value in publishing them? So, and the second question we'll ask later is how complete are they? And we'll get a quick update on what the status of them is from the editors. But first, before that, we would like to figure out what are the views on actually publishing this work? Should we progress it as an informational RFC, or should we let it expire? And that's for both the requirements draft and the testing and evaluation criteria draft. And feel free to answer the question differently for those two drafts.
This is Ben Campbell. You have a third choice, something like the Workgroup Wiki, or
Okay.
so letting it expire doesn't have to mean it goes away.
Yeah, I guess the notable thing is that we wouldn't reference. I think the big question in my mind is whether or not there's value in referencing this from whatever normative RFCs the group generates. So if we generate a codec and there's a need to refer to anything in the requirements or testing drafts, that I think would be a key question for people to give an opinion on.
Okay, so Jose, actually one of the authors, he's in the microphone queue here.
Yes, thank you. Can you hear me?
Yep.
Yeah, I just want to say that you just said if we release the, I didn't hear what you exactly said, Mo. If we release the codec, I mean the codec will be released, right?
The statement was that if we publish a codec specification, that would be a normative standards track RFC, whether or not there's value in referring to informational RFCs for requirements or testing methodologies, whether or not that's important. And if it's not, then there's probably not a good reason to pursue publication of them. If there is, then there probably is a good reason to try to publish them.
Right. So if we publish a codec, then definitely I believe that there's value in referencing all of these documents that either spell out requirements or testing.
And just Tim Terryberry from the floor. Just as a point, the RFC for Opus 6716 did actually reference its informational requirements document. Did.
Okay. So I'm hearing for requirements at least some level of support for pushing that through to RFC.
Alyssa Cooper, just so people are aware, the ISG put out a statement about requirements and use cases and problem statement type documents earlier this morning. So that might be worth taking a look at. You guys are basically doing exactly what the statement suggests, which is that working groups should think about whether they really need to publish these in the ISG stream, and should develop their protocol work in parallel with these documents and not do things in sequence, which you've obviously been doing, and kind of recommends against publishing these as RFCs if the group doesn't have like a good rationale. But I think the fact that you're talking about it and may reference it gives you leeway to be able to justify whatever decision you come to. So I wouldn't be concerned about it, but it might just be worth taking a look at that so you know how the ISG is looking at these things at the moment.
Was there any short summary of what criteria they thought would be useful?
Yeah, it doesn't really specify criteria either. It's more about the process that groups should be using if they have these kinds of documents in their queue. So
It sounds like kind of a don't publish it unless you have a reason, and you come up with the reason.
yeah, I would say that's true. I mean, it wasn't really motivated by this kind of use case. It was motivated by groups which seem to get stuck, like serializing their work, doing these kinds of drafts first, and then the protocol work lags and so on. And that's not really happening here. So.
Okay, thank you.
Ben Campbell speaking strictly as an individual. I think one thing to consider is what's the archival value of the information in the requirements documents. It's one thing to reference them in the solution to say you met the requirements. That's doesn't really have a huge amount of archival value, but if there's explanatory material and things like that in there that help people understand the solution, then that's a completely different story.
Mosinati from the floor, Mike. I have a stronger position on the testing document. I think there's a very good need to progress that and publish it because I think there's going to be extensive references from many of the codex specs into it, and there's you need to know what you're optimizing for when you're creating these codecs, and not really having targets and defined criteria is to me would be strange. So each of the codex specs would actually have to have all of this information in them, which doesn't seem to make sense. It'd be better just to reference the information once, and it would already have the explanations of why a metric that's objective versus more perceptually oriented would be a good justification for including a tool that's giving objective gains versus a tool that's giving, mostly subjective gains. So I think there's a lot of good reasons to publish a testing draft. The requirements, I think there's some weaker justifications to publish it, mostly around, why certain tools may be needed when they don't directly help the testing metrics. So it's easy to justify all of the tools that directly give you gains, directly give you, objective metrics gains and subjective quality gains. But then there may be some other tools that don't actually give you gains in any of those, but they're still useful anyway for things like error resilience or for parallelism. And instead of having to discuss all of the needs of, of those quality impacting tools, it's good to just reference them in a requirements document. But I would say that's less of a concern for me.
Okay. So I'm hearing no outright opposition. I'm hearing guidance about make certain it's necessary, and I think that there are some fairly good reasons that there's a benefit here. So would anyone like to speak up in favor of the position of not publishing these? Okay, I'll take it. We had. No, she did that last time. So we already actually had this question raised in the list. There was one person. Sorry?
Lost the screen.
Oh, we did again. There was one person spoke up in favor of it. It was otherwise silent. I would say, we can take this to the list, but there's probably going to be very little additional comment. So I suspect what we'll do is sometime in the next few weeks, put together a shepherd write-up on these and put them forth, presuming that we think they're done at this point. So. Yes.
Wiggle your dongle.
No,
No,
it
it was
was
working
working.
before.
It's
Yeah.
just we've got
I think your timeout, maybe your screensaver timeout did
no,
something.
because this has been on the entire time.
You want me to try to switch?
There we go.
Yeah.
All right,
Screensaver.
so that's the end of this, and I presume you're going to cover the the slide deck, yes?
Oh, well, we can let Jose speak to it if you want to. Jose, if you want to talk to your requirements update. He's in queue.
Yes, I would like to.
Okay.
Can you hear me?
Yep.
Okay,
We're on
great.
your first slide.
So thank you. I can see that. So the changes from the previous version 02 were very minimal. I guess the most important one was that originally we had 12 QP points for the evaluation, and we decided to only have 10. So that's really the major change. So if you could go to the next page, I will go very quickly on what we did over this past few months. So there were 3 main parts of the document: overview of applications, use cases, etc. There were no changes in that. Then a section on the requirements themselves, and then the evaluation methodology, which were minor changes. So next slide, please. So the basic requirements, and I can't see that too well, so let me pull out my own copy here so that I can talk to that. The basic requirements, essentially what we changed, we agreed that the bitstream specification should support independently decodable subframe units, kind of like slices or independent tiles, but we don't necessarily say that that's exactly what they have to be, but they must be independently decodable. And so it should be possible for the encoder to restrict the bitstream to allow parsing of the bitstream after some packet loss. So we had quite a bit of discussions on that and how to specify it and how to communicate it to the decoder. So that was really the only change in the basic requirements. So to be more explicit as to packet loss, partial packet loss. And then the optional requirements, there were no changes at all. So next, please. So yes, so as I was saying, the really major point, I guess, was that we decided that the number of QP points was reduced from 12 to 10 to simplify and to be able to better and more quickly assess the quality. And we decided that we will perform that alignment only on 4 QP points. So now we have the same as before, 3 different sections for low, middle, and high, and then 4 QP points, and the ends overlap basically. And so we also continue to use PSNR and MS-SSIM for basic quality assessment. So essentially, we simplified the process so that it can be done more efficiently. Next, please. So that's basically it. So essentially, the conclusions were that, as you can see here, we tried to take into account all the comments that we did over the list. And so that's basically it. Thank you. Any questions?
So first one comment, I think there was I think Thomas Dade, who was not here today, I think he sent out a comment on the list after your last update. Maybe you want to check that. And oh, he is? Okay, I can't see.
Yeah, he is remote, I think. So Thomas can speak to that if he wants.
I think you'll have to leave the line and let Thomas
Okay,
chime in.
I'll do that.
All right, am I in front? Thomas Stadium, Missoula. I sent a couple comments. They're all minor issues. I mean, I think it's ready as is. It was just a couple wording things.
So just as a reminder, we did last call. This was August, and so we're basically at the other end of last call. So if there's anyone who thinks this is not ready for publication, please stand up now. Otherwise, like I said before, we're going to go ahead and write this up and send it to the IESG.
And even if you don't have objections, it would be great to get some more reviewers because we haven't had much feedback on this at all. And it's, a pretty important document to make sure that we have the codex looking at the right set of requirements. So if we can get more reviews, that'd be great.
Does anyone want to volunteer? Yeah, I'm keeping looking back and forth between the implementers here. Okay, well. I mean, I guess we could try it. Tim, is there anyone on your team that we could convince to? I mean, obviously, Thomas looked through things.
Yes.
Okay. All right. Great. Thanks. I mean, ideally, we want to get this out the door relatively quickly. There's not any hard deadline, but just in a matter of, getting things nailed down.
And sometimes one new fresh read is really useful rather than someone who's looked at, 4 iterations of this from the very beginning.
All right. Thanks.
Tim will cough up a volunteer to review, at least one reviewer.
So we're not deciding to bring it for publication.
It's subject to the outcome of those reviews. It sounds like there is a wording change that Thomas has suggested, so there'll probably be at least one more revision before we pub rec it. And I think it's like what I'm concluding here is we will have probably Tim have one more person review it, updated according to that and Thomas's input, and then do a pub rec as soon as that new version comes out. Yes.
There's no decision today to publish it.
Right. Thanks. Okay.
Why did the data tracker say that version 3 of this document was published once?
That's a good question.
It says that.
It's wrong.
Maybe we ought to troubleshoot that.
Because the tool sprint had 5 people?
Jonathan, I was just commenting that the data tracker shows version 3 of this document was published both on August 4th and on September 21st. So that's a little perplexing.
August 4th is when we issued the last call. That was when we sent out the work group last call.
The data tracker history of NetVC requirements. Anyway, that's not this group's problem, I guess.
Right. Cool. No, that's. Can you send email to the tools team about that?
Did you change the state to something when you issued the last call?
I might have. Tim?
All right. I'm going to talk about the latest revision of the testing draft, which Thomas Dady is the author for. And while he is here remotely, he asked me to present in person.
A little more into the mic.
Yep. Sorry. That better?
Maybe tilt it up, tilt the mic up. There you go.
How about that? Okay, excellent. So I will do my best job, and Thomas will interrupt me if I start telling any lies. So they're two basic things: metric updates and range updates. Slide. So for the metric updates, we have removed FastSSIM entirely and replaced it with regular MSSSIM. So we re-implemented MSSSIM from scratch, referencing several of the popular implementations of it. And in doing so, we found some bugs in the FastSSIM implementation, which we'll talk about more later. But the speed difference between the two is relatively small compared to how incredibly slow all modern video codecs are, at least in the development versions. So we didn't see a point in using the fast version. Slide. We also updated the text on VMAF, which is the metric proposed by Netflix. One point of clarification was that unlike SSIM and MSSIM, where we do this log conversion to make them give numbers that look vaguely like PSNR decibels, For VMAF, we just use the scores directly, and that matches the methodology that Netflix themselves used in their own studies. Next slide. So we clarified some of the specification of the quantizer ranges to use. So for individual tool testing, we now list 4 explicit quantizers. And for the final requirements testing, we matched the update you heard of in the requirements draft with 10 specific quantizers. And that is a change from the previous version where we just specified the minimum and the maximum, but not any of the points in between. So now we're explicit about everything. And I think that is the last slide. Oh, sorry, one more. So I think this document is not quite done yet. We wanted to add a few more clips. One specifically at very low resolutions, just because some of the important use cases are dealing with very low bandwidth situations, and so you want your scalable video to go all the way down to 240p. And then on the other end, we also wanted to make sure we had at least some HDR sequences in the baseline test set. So we were not able to get that finalized in time for the IETF draft deadline, but you can see a preview of the sequences that we're planning for that at that URL. And that, I think, is the last slide.
Mo from the floor mic again. Question on the Netflix metrics. So now those are incorporated into the testing site, the Are We Compressed Yet testing site?
So I think they are not yet incorporated into Are We Compressed Yet. So Netflix has published the source for their metric, but it doesn't take input in the same form that we have all of our test sequences stored in, and so we need to modify the input modules, and that just hasn't happened yet.
Okay, so what the testing draft says now is just how to use that metric.
Right.
But nothing is actually using it, and nothing has actually generated numbers out of Dollar or Thor or anything else yet.
Yeah, we wrote a specification before we implemented it. I know, that's unusual at the IETF.
Okay, but is there a plan to implement it?
Yeah, it is on our to-do list, so we'll get it up there at some point. It's just a matter of typing.
Okay.
Yeah.
All right. Thanks. Oh, here we go. Thank you for noticing.
Thomas Day, Mozilla. I was just going to mention, I run the tool locally with just using converting the input formats myself, and it works. Like you can implement it as is. I just have I posted on the Jab Register work in progress patch, so that's hopefully coming very soon. So it is actually possible to implement a draft as is. I just haven't done it on the main website yet.
Thanks. All right.
And we have Jose also.
So what we're hearing from this is that you don't want to finalize a testing document yet. You think there's still some significant changes to come in?
Yeah, so I think in addition to the updates to the test sequences, at some point we're probably also going to want to think about testing things like rate control, and we don't have a test procedure for that yet. So as we flesh out our rate control experiments, I think we'll come up with good criteria for that and add them to the document.
So what do you think the timeframes for that might be?
Probably at least 3 months.
Okay. All right. Thanks. Jose.
Yeah, thank you. Just a very quick thing, going back to the requirements. I believe that we included Thomas's comments, so I'm going to ask Thomas to please, later on to quickly take a look at the document and make sure that we included your comments, Thomas. So that's basically it. Thank you.
Thanks. Okay, Diner.
Okay, so I'll go through the changes in Thor since the last meeting, which is not a long list, but in terms of number of changed code lines is probably the biggest update between any meeting. Next slide, please. And the most important change is that Thor now supports 10 and 12-bit video input. And of course, it also have then support for high internal precision, but that can be set regardless of the input. And we've added quite a few optimizations. And the source code has been reworked a bit to allow different bit depths while staying reasonably efficient. Next one. So the input video can be 8, 10, or 12 bits, and so can also the internal bit depth, but that can be set totally independent of the input video. So we can then have a compression gain for 8-bit video if the internal bit depth is higher, but it adds something like 30–40% more complexity on the encoder side and slightly more on the decoder side. And it's also possible to encode 10 and 12 bits video with 8 bits internal bit depth, which reduces the complexity, but basically you destroy all the benefits that you have from high bit depth. So you're probably desperate if you do that. And the video bit depth and the internal bit depth are signaled in the sequence header. Next one. So as I mentioned, there's a gain to be had if we encode 8-bit video with a higher internal bit depth. So these are the numbers that we get for 10 bits internal depth. All these sequences are HD, and on average, we get 3.8 gain. It's slightly less for lower resolutions. And the best gains are had for the high bit rates, which I suspect is that the reason for that is that at higher bit rates, the rounding errors are become more important. Next one, please. And if we move up to 12 bits internal bit depth, the gains are slightly better, 4.3%. And it's a result of both reducing the bit rate and increasing PSNR. Next one. Moving on to how it looks in Chroma. This is the U component, and then we get quite good gains, almost 13%. But these numbers have to be taken with a grain of salt, because this is BDR calculated using U PSNR and a bitrate dominated by Y. But it means that the Chroma PSNR goes up quite a bit. So it's the gains are definitely higher for Chroma. And the next one, please. And these are for the V component. It's almost identical numbers. Again, almost 13%. And I think the reason is that the contrast in Chroma is smaller, so then rounding errors become more critical. Yes, Mo.
Mo from FloorMic again. So I was surprised by how large these numbers were, and actually shocked by the Chroma numbers. I couldn't believe that much gain was possible just from a simple 1 or 2 bit, 2 or 4 bit extension. So it made me wonder whether or not we think I'm assuming this is just straight PSNR gains, right? Straight PSNR BD rate gains.
Yeah, compared to Luma, it's you're seeing the increase in PSNR reflected in those numbers.
Right.
Since
So
the bitrate is the same.
I guess what I'm wondering is, are these just the imperceptible gains that we think maybe a subjective metric wouldn't be as favorable, or do we think that this is really a good quality gain? Because the numbers suggest pretty dramatic quality gains.
Quite often, Chroma numbers aren't reported at all, since we spent few bits on Chroma anyway.
But even go back to the Luma ones. Even the Luma ones, especially for video conference, is simple content. For simple content, even the Luma was pretty high. It had like 8 and wait a minute, yeah, 8 and 16 percent bitrate savings. That seemed pretty high to me for a simple 2-bit.
I don't have the numbers for, say, H.265, but I suspect that they would be similar, since we have the same transform. You can do the exact same thing in H.265 by just upsampling the video input and then pick a higher profile and do things in 12 bits, and then at the end reverse the process and calculate BDR. But I don't have those numbers, but I think they are similar.
Maybe it might be useful to try to run the perceptual metrics too, and see if MSSim gives us anything, or if we can ever get VMAF running, see if that gives similar gains.
But those high chroma numbers make it tempting to perhaps shift the chroma QP, so you take some of the gain from chroma and put it into luma instead. At least it's something to consider.
Tim Terryberry from Mozilla. Yeah, I think computing PSNR or computing BD rate changes using PSNR from chroma, but total bit rate for the sequence is basically garbage. 80 to 90% of your bits are in the luma component. So if you change the luma component in some way that's independent of how the chroma changes, then your whole curve will shift by large amounts, like you saw.
Yeah. So,
and that's not telling you how the chroma quality changed.
So that's why I said those numbers had to be taken with a grain of salt.
Yeah.
But
so
the chroma piece now did go up.
The Arway CompressJet has a metric called CIEDE, which is the CIE color space delta E measurement, which is a very PSNR-like measurement, but actually takes color into account in, attempting to use human perceptual judgment of color to estimate distances. And so I think that is a much more reliable metric to evaluate whether or not you are improving or actually improving luma and chroma versus just, I shifted a bunch of luma bits and then, something else happened to my chroma curves.
Yeah, I tried to get the numbers from Arway CompressJet before the meeting, but it's the Thor code seems to have bit rolled a bit, so I think Thomas has fixed it now, but I don't have the numbers.
Good, Tom.
Tom Stady Mozilla, I do have the numbers. It's about a 6% gain on CIDE 2000, so still quite large.
Okay, thank you. Okay, next one, please. Yeah, so supporting higher bit depth, that means some adjustments to the code. So the things that had to be changed were that the shift after first pass of the forward transform had to be adjusted according to the bit depth, and the shift after the second pass of the inverse transform, and also the strength of the constrained low pass filter. So when we had 1, 2, or 4 in 8-bit video, that has to be adjusted to 4, 8, or 16 for 10-bit, and likewise for 12 bits. And also the same thing for the threshold and beta of the deblocking filter. And of course, we have to adjust the pixel clipping. Whereas the quantization and dequantization are unchanged, meaning that the QP range remains the same. And that makes sense for me from a user perspective. I think H.265 is doing it differently. I guess it really depends on whether the increased bit depth is for increased accuracy or for higher dynamic range. But the user can always change the QP in the application and do whatever he thinks is right. So these are small changes on paper, but they have large implications for the source code because we want to have optimized source code. Next one, please. So we have a bunch of optimizations for 8-bit frame buffers, and we want to keep those. So the source code had to be changed to handle both 8-bit frame buffers and 16-bit frame buffers. And if we had been doing this in C++, this would be easy to implement using templates, but we have written for in C99. So instead of templates, we use preprocessor magic to mimic C++ templates. So much of the code in the encoder and decoder now gets instantiated twice, once for 8-bit frame buffers and once for 16-bit frame buffers. The key is that the amount of source code remains roughly the same, but the executables increase in size. Next one. So Thor uses an abstraction of common SIMD intrinsics to support SIMD optimizations for different architectures. The reason for this is that we just want to write SIMD optimized code once and have good results on multiple architectures. So this was something that I presented in Yokohama a year ago. And this is not required for standardization, but it's still useful to assess the complexity in real applications, and it also makes the reference codec more shipping ready. So we have a lot of SIMD optimized code for 8-bit, and now it suddenly needs a counterpart for high bit depth. We have several thousand lines of code, so this is possibly a large task. It takes a lot of time to write code like that. Next one, please. So instead of spending weeks or months on writing such code, it's possible to convert the existing code automatically and get reasonably good results. So for instance, if you have an intrinsics like an 8-lane 8-bit add, that could be converted to an 8-lane 16-bit add, and a 64-bit load becomes a 128-bit load, and so on. And in order to do that, there was a need to add a new set of intrinsics that are 256-bit wide, so that we could convert 16-lane 8-bit adds to 16-lane 16-bit add, and so on. So that was added along with native support for AVX2. Otherwise, these new 256-bit intrinsics are emulated, which is mostly by simply duplicating 128-bit intrinsics. So in the end, we end up with just one set of SIMD optimized code to maintain regardless of the bit depth and architecture. Next one. But it needed a few changes of the existing code to make that possible. So rather than writing new code, I reworked the existing code. It's just as fast as before, but it's now trivial to convert, and it's just a matter of search and replace done by a sed script. And now that we have even wider intrinsics, we also have the door open to add AVX2 optimizations even for the 8-bit code, but that has not yet been done. Next one. So just to have a summary of the input formats that Thor supports now, that's 8, 10, and 12 bits video, and we also have 420 and 444 chroma sampling, which was added before the last meeting. And we have basic SIMD optimizations for everything. Still a few things that's not directly supported, but it can be trivially handled, like interlist video and RGB 444. And we also have updated GitHub, so it's possible to download the latest changes and play with it if anyone wants to do that. And finally, next one, please. These are exactly the same curves that I have shown before, so this is just a reminder. There's no big changes to these plots since for a proper apple-to-apple comparison, I can't use the gains from higher internal bit depth in this plot, since you can do the same thing with H.265 and VP9, and the gains I suspect would be quite similar. So this basically shows what Thor is good at and perhaps not so good at. One axis is the frame rate and the other is the quality, and Thor is not able to match H.265 if we have infinite computing resources, but for practical applications, Thor seems to have a much better complexity compression trade-off. And this is for the low delay configuration. And if we move on to the high delay configuration on the next slide, then Thor still has a better trade-off than H.265, but it's not quite able to match VP9. At least VP9, for the most part, runs faster. But I also believe that VP9 has more SIMD optimizations, so it should be possible to rise the Thor curve a bit. So no, not a long list of new tools this time. So we could perhaps rather say that Thor has matured a bit, now supporting what it absolutely needs to support. So, yeah, any questions, things to discuss? All right. No.
So I had a point about the surprising gain for the high bit depth. If Jose could come back in the queue, I'm trying to recall, what did the requirements say about high bit depth? Because I know we iterated a few times back and forth on that. Is it just an optional requirement, or is it a separate profile, or are we baking high bit depth internal precision into the basic requirements for any candidate now? It sounds like maybe we should if the gain is really that good. Is he talking?
Jose?
Yeah. Oh, sorry. I was on mute. Yeah. So I guess your question is whether that is in the basic requirements or is it an optional requirement, right?
Yeah, and specifically allowing the internal high bit depth option, not just having 10-bit or 12-bit input sources, but can we have 10 or 12-bit internal precision for 8-bit sources if the gain is really as high as we're seeing reported here?
Right. So what we have in the basic requirements is 8 and 10 bits and up to 12 bits for high profile. So those were put in the basic requirements. Internally, there's really no explicit in the basic requirements. Also, no explicit restrictions on any complexity.
Well, if it's a requirement to have 10 bits input video, then I suppose there's no reason why not use that even for 8-bit video input, since it has to be implemented anyway. The trick really is what you do internally, not what resolution, what kind of resolution that you accept. And software-wise, there's no difference between 10 or 12-bit video in complexity. So if you have to support 10 bits, you can just as well support 12 bits and use that as an internal tool, at least from a software perspective. Tim?
Tim Terry from Mozilla. So I know you guys talked a while ago about implementing arithmetic coding in Thor. Is there any progress on that, or is that something you're
implementing?
Arithmetic coding?
We have thought about it. About half a year ago, I did some experiments. I tried a couple of ways. I actually had a couple of working implementation using that, but the gains were very small. And even if I cheated, just assuming that I would reach the entropy, the gains were quite small. So the trick here isn't really arithmetic coding, but how you do the adaptation. So currently, it's not on the agenda since the gains were so small, and there also are some benefits of doing it like we do now. It keeps things simple and good for error resilience and so on.
Okay.
Okay.
Thank you, Steiner. All right. And now Tim's going to talk to us about DALA.
All right. Can people hear okay? Good. So say that there has not been a large number of changes in DALA, but we have done a few things. The first one is that we have finally finished our fixed point port of PVQ. So that had been going on, I think, for a couple of meetings, but is now done. We also ported PVQ over to AV1. And so we had some interesting results there that Yushin's going to talk about in his presentation afterwards. So I won't spoil his thunder. The DALA entropy coder had also previously been integrated into AV1 and is now the default. And then we've done several improvements to metrics and tools, including all of our metrics now support 10-bit. And as I said in the discussion of the testing draft, we found and fixed an overflow in fast SSIM. Next slide. So let's talk about that one a little bit more. Basically, there was an integer overflow that only affected frame sizes of 1080p or larger. And so when we did our initial validation of fast SSIM, we did it on our still image test sets, which are just small enough not to trigger it. But it does, however, include some videos in NTT Short 1, which was the set of test sequences that we used to report most of our historical results. So all of those numbers have been wrong. Next slide. So this is the slide I'm sure most people here have seen before. This is the previously reported numbers for fast MSSSIM for DALA at various points in time compared to H.265. And if you go to the next slide, that's the corrected version. The one other difference between this slide and the previous one is that X265 got upgraded from version 1.8 to version 2.1 on our testing infrastructure. So we have the new numbers are with the new version of X265, and that's why you see that red curve there has changed a little bit. But most of the rest of the numbers just got a little bit worse at the high end, but the overall story didn't change very much. All right. We have also started measuring DALA with the new testing methodology in the testing draft. So next slide. So this measures with fewer points and on a different set of test sequences. And so as you can see, when we do this, also using regular MSSSIM, as I mentioned before, instead of fast SSIM, you get the results here where there is a bit of a larger gap between us and X265. So that I think that has more to do with the set of test sequences than it does the switch from fast SSIM to MSSSIM. If you look at the PSNR HVS numbers on the next slide, we still come out a little bit ahead way up at the high bit rate range, but there is also, again, a significant gap between us and X265 on this set of test sequences. Right? So you can't accuse us of picking our test conditions to make us look good. Overall, since Berlin, we've had about 60 commits. The encoder has gotten between 6 to 9% faster. And we've had fairly small improvements in BD rate. Most of that, I think, is a result of the PVQ work. All right, next slide. All right, so these are a bit more detail about the various changes. As I said, Fixed point PVQ is now finished. That was 27 of the 60 commits, so about 45% of the work. The overall BD rate changes were very small. We are still actually using double precision floating point in the encoder side, but that's non-normative, so we're not planning to fix that anytime soon. Do you have a question, Mo?
Go ahead and finish.
Okay. And in fact, we may always wind up using floats on some platforms just because when we do RDO, it is actually very convenient if the hardware has a fast reciprocal square root approximation to make use of it. And for example, x86 has that for floats, but not integers. ARM has it for both. So we could actually do that in fixed point for ARM, but we may wind up using the floats in the encoder always. Next slide.
All right, and this is what I was going to ask about. Mo Zanetti from FloorMic again. The framework that you use for your SIMD optimization. At one point, were you looking at the Thor intrinsics, or did you end up moving to something else or roll your own?
So at the moment, we're mostly just using raw intrinsics directly for every platform. We did look at the Thor intrinsics, and I think we had a patch from Steiner, and we had a bunch of review comments on it, and I think those were never addressed, so we never landed it and never converted all our stuff. But I mean, I think we'd be okay with using an approach like that, but it's not currently integrated.
Okay, because I was going to say maybe it may be good for a smaller team to figure out what the best intrinsic approach is, and especially if we can get the lift of supporting a bunch of platforms with a common library, and with the recent work for 256-bit, that would be good. And if you guys have already done work for float SIMD, that might also be good if you could somehow, I guess you probably have totally different routines. Forget the intrinsic, probably totally different routines for your float versus fixed point implementations.
Right. So, well, to be clear, this is work we have not actually done yet. So there's basically no SIMD in the actual PVQ code at the moment. But we know how the instruction sets works, and we know how we would write it if we went down that path. So like, we have not actually done a fast RDO search using the reciprocal square root approximations in SSE.
So all of the PVQ work, both fixed point and floating point, is still non-SIMD.
Correct.
Oh, okay. That might explain some of the 20x we're seeing.
It does explain a chunk of it, yes.
Okay, got it.
So we also made some algorithmic improvements to PVQ encoder speed, since, as Mo alluded to, porting PVQ to other contexts has in fact been quite slow. So we are now using an approximate rate for making RDO decisions, and we also spent some time improving that rate. This is instead of explicitly encoding the actual code words and then counting up all the bits. So this is by default off in DALA, but on in AV1, and this was about a 0.3% regression, but was much faster. And so for the next stuff, I don't know if everyone remembers exactly all the details of how PVQ works, but we have these two parameters, gain and theta, which are sort of somewhat perceptually meaningful parameters. Gain is the amount of contrast, and theta is how much like the predictor you are. And so when we quantize those, we consider several different candidates, basically rounding up and then rounding down and then going slightly beyond rounding down just for RDO purposes. And from the given value of gain and theta, we compute this codebook size k, which is basically the L1 norm of the resulting coefficient vector you're going to code. And so the larger that is, the more bits you have to spend coding that coefficient vector. So when we do all of this, we consider all of these different candidates, and in order to speed that up, we now sort the different gain and theta candidates by this value k, so that when we do our codebook search, we can reuse the previous results and just add more pulses. to the previous vector instead of starting our search from scratch each time. So we also get to skip the search entirely when k is the same for different gain and theta candidates. So this, in addition to being faster, also gave us a small, less than 0.1% improvement on VD rate. And then finally, any gain and theta candidate that can't possibly have a lower distortion than just the skip candidate, we don't bother to actually search anymore. So that's assuming, given the distortion introduced by quantizing gain and theta, assuming the distortion introduced by quantizing all of the coefficients is exactly 0 and some minimum rate over what the rate we would have to code for skip. If all of that is still worse than doing skip, then we just don't look at it. And said that has no metrics change because we're not considering that something that can't possibly help. Next slide. We also made a number of changes to the deringing filter. These have actually all been changed in AV1 but not ported back to DALL-E yet. So the first one, we use a shorter 5-tap filters for chroma. So if you look in Objective 1 Fast, there's one particular sequence, Minecraft, where we were showing fairly large regressions by turning deringing on. And so using the shorter filters makes those regressions go away. The overall changes for the chrominance metric I mentioned earlier, CIEDE, was very tiny. So we didn't lose any quality in chroma anywhere else by using these shorter filters. And the shorter filters are basically just because chroma 420 is subsampled. We also now support 422 input, but we did that by just disabling chroma deringing. So we thought that was preferable than trying to do something more complicated. The main issue being, since our deringing filter is directional, if you subsample to 422, the directions in the chroma plane don't line up with the directions in the luma plane unless you stretch things. And stretching things was, as I said, complicated. So instead we just disable it, but that makes chroma slightly worse for 422, but if you care about that, you should use 444. We also simplified the threshold calculation for the second filter. So this used to be based on the amount of change in the co-located pixel in the first filter, and instead we now base the threshold on the total change made by the first filter. So in that second filter, we no longer need to look up what the change was on a per pixel basis, and so that saves a bit of computation. And it was a tiny regression, but I think the amount of computation it saved in the decoder side was significantly larger than the regression on the metrics, so we thought that was a good simplification. Next slide. Sure.
Mulligan from the floor. On your 422 comment, I'm a little confused about what happened there, because I would think that anything sensitive to the size of the block would be impacted by 422, and so I would think you wouldn't change the size of the block. You would just have more blocks. You would just have 2 chroma block, 4 chroma blocks instead of 2.
The problem is not the size of the blocks. The problem is the direction of the filter. So the way it currently works is that we estimate the dominant orientation on the luma plane, and then reuse that orientation for the chroma planes. And so we support 8 orientations in the luma plane. And if you now go take that to chroma, because the chroma is only subsampled in one axis, your directions get stretched. Particularly the diagonal directions get stretched.
But don't you look at the actual block, not the entire plane? You're just looking at block by block, right?
Correct.
But wouldn't you just use two separate chroma blocks with 2 separate codings for that?
Well, that would mean you'd have to do a direction search on chroma. You have to do 2 direction searches on chroma. Currently, we only do 1 direction search on luma and reuse it for all 3 planes.
Okay, but I would think you could still take that one and use it on the 2 separate blocks independently, because those blocks are square if you look at 2 of them. They're rectangular if you combine them into 1, but they're square if you look at 2 of them.
Right, but if you find something that has a 45-degree angle in Luma, then it does not have a 45-degree angle in Chroma when you do 422 subsampling. Right? It's either 22.5 or depending on which 45-degree angle you talk about. And so we'd have to come up with a whole bunch of different filter step sizes and directions and lookup tables just to handle the 422 case, to make the directions match what the actual direction was found in Luma, and that just didn't seem worth the extra complexity.
Yeah, so the reason I'm not that sensitive about this particular filter, but I just wonder for 422 in general, seems like all the coding tools that are sensitive to size would have this similar issue, right?
I think it's not so much size as it is direction. And so at least in AV1, for example, like intramodes are directional, but the Chroma plane has a separately coded intramode than the Luma plane, so it doesn't have this issue. The problem here is we're trying to reuse something from the Luma plane for the Chroma planes that is directional, and it didn't seem worth trying to do the conversion to account for the fact that the directions all get skewed.
All right. Well, like even Thor had the Chroma from Luma prediction in the last meeting that was presented. It seems like even that would be a problem for things like 422 if you wanted to use predictors directly.
Yeah, so you wind up having to, whatever your subsampling is has to account for that correctly.
We should make sure the requirements say don't support 422.
I would love for the requirements to say that. Anyway, next slide. So we also did some significant optimization work of the deringing filter in AV1. So we ported over all of the SIMD code for deringing from DALA. We also greatly reduced the amount of copying and buffering. And this is, so one, we made the buffer smaller and we eliminated some of the buffer copies. But in fact, the largest improvements were actually from getting better cache coherency in the way that we manage these things. So I think actually if you do an intraframe, you wind up with more copying, but since it's all out of cache, it's still faster. We also stopped running it all on blocks where the threshold was 0 so that it couldn't actually do anything to those blocks. And overall, the decoder speed impact went from around 50% of the decoder time without deringing to down to 8.5. So 3.2% of that is for the actual filter calculations, and 5.3% is still buffering and copying and managing things like skip flags. So we think there's still room for improvement there. None of the buffer copies are SIMD, and deringing is currently done in an entirely separate pass. So that could be done. That could be combined with deblocking to even further reduce cache misses. So we think there's room to move that number down. I'm not sure how much effort we will invest into doing that, but it's certainly possible. Next slide. Just small updates on the Q15 entropy coder adaptation that we discussed in Berlin. Basically, we wrote it down in this draft. If you have questions about how it works, I encourage you to go read it and give us comments. We showed it to some of our hardware partners. No one had any heartburn about it, so that seems good. We still may change and improve exactly how that works going forward. So I think Thomas Davies of Cisco was conducting some experiments that modified how this adaptation worked, which gave some coding gains. So that was encouraging. Next slide. And basically where we're planning to go from here. So right now, the PVQ integration into AV1 was just done for optimizing for PSNR with flat quantization. So we had no activity masking and nothing else. And that's just to make sure that, we were sure that the basic integration was working correctly, walk before you can run. So obviously the next step is to start turning on some of these perceptual tools. We've also been working on further tuning for visual quality inside DALA, and I think we were seeing something on the order of 2 to 3% improvements on visual metrics in DALA, but that work has not actually landed yet. And when it does land in DALA, then we'll port it over to AV1. So now that we have basic PVQ into AV1, we can start porting over Chroma from Luma. and we also plan to port over DALA's rate control. I should say that the things that we already have ported over to AV1, some of this is still pretty preliminary, so there's a bunch of work to do to improve the integration with the rest of the codec. And I think that's it. Anybody have any questions?
Steinar Midtskogen from Cisco. You're mentioning Chroma from Luma. I tried to do something similar using Thor, the Thor tool, to get that over in AV1, but I gave up on that because you can have different prediction modes for Chroma in Luma and Chroma. Is that a problem for the Chroma from Luma in DALA?
So I think yes and no. I think it's okay to have different prediction modes for Luma and Chroma, depending on how you want to go about integrating it. So we're actually considering a number of different options. One is to just add CFL as an extra prediction mode for Chroma. So it would just be explicitly coded as one more mode in the list of modes. And if I remember correctly, the stuff you were doing with Thor tried to figure this out automatically without signaling.
Yeah, there's no signaling, so that's why we get a problem.
Right. So one solution is you use signaling. The other thing we were considering is just removing all of the other modes and only using CFL, at least for intraframes, and that worked reasonably well in DALA in the sense that using CFL for everything worked slightly worse than actually trying to use real have explicitly coded inter-prediction modes, but then we didn't have to pay the cost for signaling what the prediction mode was. So overall, it came out about even, but because we didn't have to do a mode search, it was much faster. So we're going to try repeating that set of experiments in AV1 and see which way things come out. All right, any other questions? Great, thank you.
Thank you. So I can go. Hello, my name is Yushin Jo. I'm from DALA team in Mozilla. So I'm going to talk about our experience in applying PBQ outside DALA. Actually, the codec is AV1 codec by AOM. Next slide. So for recap, this PBQ is actually a perceptual vector quantization, which is already proposed for NETVC. And also it is only used for DALA codec, and we wanted to see how it is doing outside DALA. So this is basically gain shape coding of the transform coefficient as like the Opus codec. And I would say the most distinguishing idea of this PBQ is the way it is referencing the predictor. So this is also a big difference from the PBQ in Opus. Actually, PBQ in Opus is called pyramid vector quantizer. So briefly, PBQ does not use any subtraction when it is using predictors. So subtraction is actually basically difference between predictor and original signal. Next slide.
Quick question, just to clarify. So part of the motivation for this was other goals beyond just compression quality, right? You were trying to meet some of the other objectives in our charter, like the royalty-free part? Okay. And the goal was that to avoid a lot of patents, you're doing something different in the prediction space to avoid subtracting and residuals and things like that. So even if PVQ doesn't give a quality gain, there may be some advantage to looking at it for the IP aspects.
Yeah, actually, honestly, I was not sure whether I can say the IPL sense or meaning. It's okay, really? Oh,
the motivation. I mean, we can't give a judgment on it, but the motivation of the work was not purely for just gains, right?
That's actually my best motivation. So even if there's no current benefit, I mean, coding gain improvement, actually, just avoiding, I mean, risk-free for IPL sense probably is a very large benefit. And then we can go to next slide, please. So there's another slide, some diagram which shows what is the actually difference in architecture. But basically, if you want to use this PBQ, you have to apply transform to the predictor itself, because the PBQ is actually referencing the predictor in transform domain, and also the original signal need be represented in transform domain. So different from traditional video codec, where the transform is applied to residue signal. With PBQ, the transform is applied to original signal. Also, as Tim mentioned, the activity masking, automatic activity masking, which is actually very nice merit of PBQ, which is not enabled yet. So the RDO decision, optimizing the quality is solely based on PSNL. Next slide. So this is diagram for traditional architecture focusing on transform and quantization. So as you see, the residue signal is coming from the subtraction, so difference between input and predictor. And the transform is exactly applied to residue signal. And then the quantized symbols are actually going through coefficient coder, and there's a bitstream generated. Next slide, please. However, with PBQ applied in AB1, the difference is that you have actually additional transform of there, which is applied to predictor P. So you have two signals from two transform, actually, T of X and T of P. There's error tab there. And then the PBQ quantizer needs two input. One is transformed input, another one is transformed predictor. So also with PBQ, it is not just about quantization, but it's generated, the symbols are completely different from the traditional coder. So its coefficient coder is also very much different from traditional coders. And then the inverse transform is actually applied to this dequantized T of X. Next slide, please. And we have some result about coding change, coding gain. And basically there's no improvement. So I can say that I'm just happy with there's surprising changes here. So at least for optimized with PSNL, we can actually directly replace the existing quantizer with PBQ. Just the problem is that it's very slow. It's very, very slow now. For this result, we have used one of the test sequence set, Objective-1 which is actually common for both IETF and AOM. And encoding options are most intensive one. That's actually for high latency encoding. Next slide, please. Back to speed. So the reason why there's too much slow down is because PBQ itself is actually searching a lot. So compared to existing scalar quantization, which has O(n) complexity, the PBQ is basically doing n square. So also, we have only used PBQ in DALA before, but DALA's audio search space is much, much smaller than that of the AB1. So here's one example. When we have encode just one frame, first frame of the grandma QCIF in intra-frame mode, the AB1 is calling 160 times more calls to the quantizer. So the reason is that DALA does not have intra-prediction mode, like there are 10 prediction mode in AB1. Also, AB1 has different sizes, transform and types, different transform types. Or furthermore, the AB1 allows the transform size can be smaller than prediction size, the partition size. So virtually, the AB1 can be, say, 1,000 more calls to the quantizers compared to DALA. Next slide, please. And this is actual counting of how many times quantizers are called. So again, this is based on first frame only in intra mode. And the first column, speed rebel, is actually the speed CPU use option for Avian codec. So 5 is fastest one, and 0 is the slowest one, but best quality. And this is actually a number of calls are also used for debugging purpose because they should be actually very close. And second and third column is for calls to ABM quantizer and PBQ quantizer. And the last column is more some debugging purpose. That's actually inside PBQ quantizer. It is calling PBQ quantizer for each band of the whole transform block. And then they can be called multiple times when encoding one transform block. One thing probably you have question is from speed level 4 to 3, there's a big increase of the number of calls. The reason is that it start to allow the transform size can be smaller than prediction size. So that's the reason why there's a big increase. And then for Avian codec, the speed level 3 to basically the same for intra. So that's not the error tab. Your question?
Mo from the floor mic again. The speed levels that you picked, why did you stop at 5? It seems like you think the higher speed levels are irrelevant.
That's the largest one in good mode in AB1. In real-time mode, there's a 0 to 8.
Yeah, that's what the reason I ask is because currently Chrome ships with VP9 running at 7 and 8 for real time.
Oh, yeah, but
so if we care about WebRTC implementations, we should probably care about 7 and 8.
yes.
So maybe good to include those numbers too.
Yeah, actually the testing has high latency and real time. Actually, I think we are talking about the real time.
Real time, yeah,
Yes, yes.
yeah. Real time WebRTC use in Chrome is 7 and 8.
Yeah, that's right.
Stan Almitsskogen. Is it possible to use a faster approximation during a mode decision and then do the real thing only in the final encode? So you get
Yeah,
the speed up?
yes, we believe there's possible engineering and we want that, and you're welcome to contribute that part. So actually that's one of our to-do list. So instead of calling the transform quantization for every decision pass of this audio huge, if we have some nice ALDI model, that will save a lot, the time a lot.
Yeah, Tim Terry from Mozilla. That was also one of the changes I mentioned in my presentation, is that instead of actually doing entropy coding for all of these things, we can do a rate approximation, which helps save some time for this for a very small quality penalty.
Right, next slide, please. So there are some interesting issues which has arisen during this integration work, actually this experiment. One thing is that, I'm not sure you have a chance to see PBQ code. They are actually full of audio in search stage. So it is not just choose one code point or vertex in hypersphere surface of the hypersphere, but it has to actually choose best quantization point in rate dispersion sense. And then this somehow affected, breaking the balance between Luma and Chroma quality. So we wanted to actually compare the quality with AB1. Maybe this is not really worth spending time, but we have spent, the DAO team has spent several weeks to resolve these issues. So probably later, if PBQ is really adopted, then this can be some possible issue. Another one is AB1 is using hybrid transform. So it's not just DCT and DCT, but it can use ADST, so which is asynchronous or asymmetric discrete sign transform. So there are 4 different types of transform. And then PBQ want scan orders, zigzag scan orders for each band, actually sub band of the transform block. So we need to define that one. So we actually have some tool to convert from AB1 scan order to our purpose. Next slide, please. And our future work will include enabling this automatic activity masking, and then also need to enable the high bit depths. But as Steiner said, this is very simple in Word, but it's very large work in source code. And again, this audio model will save the time a lot. Next slide. I think this is the last one. Oh, yeah. So, yeah, it's a reminder that the PVQ was originally proposed to this NetBC last year, summer, IETF. Okay.
All right.
That's all. Any
Questions, comments?
Or comment? You can speak in Korean.
So it's encouraging to see a tool moved from across codecs. That's I think is it the first tool that we've seen move across codecs?
De-ringing.
Yeah.
Okay, yeah.
The de-ringing is also, yeah. Jambox de-ring.
Cool. Well, thank you very much.
Thank you.
So that takes us to the end of our planned agenda. Presuming no one has come up with any additional items they want to discuss, you're going to have the rest of the afternoon off. So thank you very much for showing up. Please make certain if you didn't put your name on the blue sheets to go ahead and come up here and do that. Otherwise, have a good evening.
Just in time for happy hour.
Yeah.
Anybody need a blue sheet? Anybody not get a chance to sign the blue sheets?
And then the second filter we require because you might be